I think you're ready to try one of these on your own. A kite 100 feet above the ground moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been let out? I want you to draw a picture and write down an equation that connects variables in the picture before you differentiate. Get all that done and then come back to check what you got, and then you're going to take a derivative after that. So I've got a string anchored to the ground, and a kite is 100 feet above the ground, and it is moving horizontally. Amazingly, it's not going up or down. It's just moving horizontally. It's a fascinating kite. And there's a point at which 200 feet of string has been let out. That's going to be the hypotenuse of a triangle. And as the kite is moving, this side of the triangle that I've labeled x feet is increasing. Now that we have our picture and our labels, let's go back and look at what it is we're trying to find. We're asked about at what rate is the angle decreasing. In terms of calculus, what is it that we want? We want d theta dt, which means I need an equation that includes a theta. Now, we may be tempted to use the x and the d and the theta. And I mean, we could. If we did, we would have the cosine of theta is equal to x over d. But then when I differentiate on the right-hand side, I'm going to have to use a quotient rule, and I'm going to have differential, or the dx dt and dd dt coming out. It's going to be kind of a mess. I don't want to do that. We might next consider using the 100 feet and the d, and that would give us the sine function. The sine of theta is 100 over d, and hopefully you got, by the way I introduced this, that that's not the way we're going to go. Now, aside from the fact that d is in a denominator, when we differentiate both sides of this, we're going to end up with a dd dt again, and that's not something that we have. That leaves us with using the 100 and the x. Now that doesn't involve the d, but that's going to be okay, it turns out. And I'm going to write down something else that we're not going to use. I know. Tangent of theta is equal to 100 over x. This is what we're almost going to use. But look, if I differentiate the right-hand side of this, I'm going to have to use the power rule, and I'm going to end up with an x squared in the denominator. I don't want to do that. What I would rather do is use a reciprocal. See, we have a lot of choices with trigonometric functions, and so I like to go for the path of least resistance. If we spend some time getting a thoughtful setup, then our work can be a little easier. And here I'm going to use that the cotangent of theta is equal to x over 100. The derivative of the cotangent is the negative cosecant squared of theta, but don't forget we're differentiating with respect to time. So I have negative cosecant squared of theta times d theta dt. That works out because that's what we're after, d theta dt. On the right-hand side, I'm going to pull the denominator of 100 out front as a coefficient, so 1 over 100. And then the derivative of x with respect to t is dx dt. Now that works out because in the statement of the problem, we were told 8 feet per second was the horizontal speed. That's our dx dt. So I'm going to solve for d theta dt. And I'm not going to divide both sides by cosecant squared of theta. I'm going to multiply both sides by the negative sine squared of theta. So I have negative sine squared of theta over 100 times dx dt. Now I'm ready to plug in some numbers. 100 is 100. Okay, fine. dx dt we just said is 8. What about the sine of theta? What do we have to do to figure that out? Well, folks, look. The sine of theta is 100 over d, but we were supposed to find this when d is 200. If d is equal to 200 feet, then the sine of theta is 1/2. So when you take everything in, it doesn't need to be so bad. We don't even need a calculator for this. D theta dt is equal to, look, 1/2 squared is 1/4. 1/4 times 8 is 2. 2 over 100 is 1 over 50. So negative 1 over 50. I have no units here. That's when we bring in a dummy unit. D theta dt is negative 1 over 50, radians per second. So then we can say the angle is decreasing at a rate of negative 1 over 50 radians per second. In case you're curious, that's about 1.15 degrees per second, or I guess negative 1.15. So every second it's getting smaller by about 1.15 degrees.